Jon from Ekkono, who has brought, I think, Sebastian, is it?
That's correct.
Yeah, that's right, online. So take it away.
So am I standing between this crowd and drinks right now?
Yes, exactly.
Wow, that's gonna be a tough one. Well, thank you, Magnus, and great to be here. My name is Jon Linden, CEO, co-founder of Ekkono Solutions, and as Magnus said, we've been a long time Things member, and it's great to be back at an anniversary. Been missing this, been missing meeting people in person, so really nice. What we do is we're a software company. We do edge machine learning. We're based on over 7 years of university research at the University of Borås when we founded the company in 2016. And what's unique about what we do is that we can scale down to run on super small devices, and that we actually do incremental online learning at the edge. And you will see where that comes into play and how that's being used. And that's today being used by customers and companies like ABB, Volvo, Alfa Laval, Husqvarna, that are customers of ours. And as you can tell, they are in different industries. We have industrial equipment, we're talking automotive, energy, but today we're going to talk medtech, because we're very proud to actually add a company called Peninsula Medtech, or Pen Medtech for short, as we refer to them, to that prominent customer list. And what they do is ventilators, a kind of product that really got on everyone's awareness during the pandemic for natural reasons. And they are really a front runner in developing a new kind of ventilators. So with me on link from Devonshire, I have Sebastian Brown, the CTO and founder of Pen Medtech. So welcome, Sebastian.
Hi, Jon. I take it you can hear me then, yeah?
Yes, I
Great,
can.
Excellent. Hi there. Hi, everyone. I'm sorry I can't be with you today, but so yeah, my name's Seb. I'm a doctor in anaesthesia and intensive care, and I've worked as an entrepreneur in the medtech space over the past 6 years, developing technologies in critical care. And I got drawn into the COVID pandemic response in the UK to design ventilators, and we ended up in the final stages of this process with some really big UK companies. And so we started PenMed at the end of that process to develop the next generation of ventilators and anesthesia devices. And this was kind of focused around answering questions that the pandemic had thrown up about how current devices limited our ability to respond to the pandemic. And in the initial phase, that cost quite some number of lives. But actually, this was all stuff that we already knew, because actually the current devices limited the way that we worked pre-pandemic and were costing lives then and actually still doing exactly the same thing now. And our device addresses these issues to reduce patient harm using modularity and provides an unbroken platform to implement machine learning that we're then going to use to improve patient outcome and reduce costs to healthcare. And so I wanted to focus for this presentation on just one issue that we had during COVID. And that was not being able to use our anesthesia machines outside of theatres to provide ventilation on the wards or in ICU or in transport. And so we've have a lot of anesthesia machines in different hospitals, and we really wanted to use them for COVID patients when things went wrong. But we realised that no one was familiar, and also that they all needed compressed air, which wasn't available in the locations of use. And so often they're using compressed air because they use the mass flow principle, and the device that we built used the mass flow principle. So we've got essentially air and oxygen, and they've got a valve and a flow meter each, and you mix them together to generate pressure for the breath and also the right fraction of oxygen for that patient. But as I say, there's not compressed air on the wards, and it's not available when we transfer patients. So we knew for the device that we wanted to build, we wanted to move from our valves to a turbine, which you can see a little picture of. It's a really small thing that you might find in a vacuum cleaner, essentially. Now, we thought this might be a relatively straightforward process, but we were unfortunately quite wrong. So what we're actually trying to achieve when we ventilate patients is a relatively square trace, square pressure waveform. So I've put this in the graph on the left, and this is basically in dark blue is the pressure trace. And so you're looking to achieve, have a reasonably rapid rise to a very steady plateau, and then tail off and let the patient breathe out, basically. And it generates the flow profile, which you can see in the lighter blue there. And so the issue we had is that we'd gone from a device that was relatively linear, the valve with a small hysteresis, low inertia, rapid response, to a device that actually had a really quite a big lag in it, significant inertia, and a very different performance when it was accelerating and decelerating. And so we'd gone from this kind of linear system to this really non-linear system. And we were talking with Ekkono anyway about integrating machine learning in our device, and what that potentially could mean for healthcare. And so we basically decided we might try and dump this problem on Ekkono rather than solve it ourselves, because it was so complicated. And so we really used it as a way of actually working together. And we wanted to achieve three things. One was to help us understand the problem and how we might tackle it using machine learning. We wanted to provide a means of control using machine learning. And we really wanted to understand what were the capabilities and what was the flexibility of the Ekkono solution. Okay, go for it, John. Next one. And so I'm going to kind of skip the entire development process and go straight to the end. And what actually we ended up with was we used a data-driven neural network model of turbine dynamics so that we could feed forward and account for that lag, and be able to generate a relatively square wave pressure trace. And we do some other things to straighten this completely using other valves and stuff. But if you do too much of that, you're just wasting oxygen. So you want it to be pretty good. But what you can see here is that we're generating an output for the turbine, which is the orange trace. And we're generating that, and there's such a lag that actually that basically we are actually reducing the turbine output before any pressure has been generated in the system at all. And then we have a second peak to make sure there's not too much undershoot. So you can see the effect of the lag is you've switched on the turbine and given it an output, and then you're already reducing it before it's even really had any effect that you can measure in your sensors. And so this sort of feed forward system with this real planning was needed, and a neural network model which was incrementally trained was a fantastic way of doing it. But then obviously what happens if the patient coughs? So actually we also used another feature of Ekkono, which was the model predictive control, to predict the pressure horizon 50 milliseconds in the future. So if the patient coughed, it would anticipate what would happen to the pressure, and we could do something about that in that time period. And so the Ekkono system gave us multiple different tools that we stitched together and actually got the performance and the flexibility we needed. And sorry, next slide, John, if that's okay. And so I guess one of the key aspects I wanted to talk about working with Ekkono and their system was, obviously it was great to work with them to understand the system, share information, build models. But what really made a difference for us was actually we were then able to put them using a PC. We were able to run those models on our pneumatic and mechanical hardware. But then we were also able to cross-compile that and put it onto our embedded hardware immediately. So that was then looking at, okay, what's the resource consumption? How do we make sure that using these machine learning automation technologies work on our embedded hardware and actually are safe? Because what we don't want to do is run a machine learning script and find it accidentally crashes the ventilator and switches it off. So, all of this architecture stuff is really important. The ability to be able to do this iterative process of build the model, test it on the mechanical hardware, test on the electronics hardware, make any changes, that was vital for us. And so I think the platform independence and the capability and flexibility of the Ekkono solution enabled us to achieve the three aims that we set out to achieve. And that's where we are.
Thanks, Sebastian. I think this is a very good case where edge machine learning comes in handy, where you can actually run it on the device. And what it boils down to is that you can learn those individual conditions. In this case, we're talking about learning and understanding the individual patient and how they breathe. In other cases, it might be a question of the environment, the climate, the conditions, the application, the load the product is operating in, like a pump. The same kind of pump can be used in a skyscraper to pump water or in a brewery to pump beer. What's normal is going to be different between those two different installations. Or let's take like a gas turbine that can be used in a high altitude in a very dry or cold climate, but it can also run on an oil rig at sea level. The oxygen mix will be different. The conditions will be different. Or an heat exchanger, where one can be running outdoor on a ship, heating up oil, while the next one is cooling just water in a dairy. So they're used for very different applications. And we see that companies more and more start realizing that when they start digitizing products, when they start switching over to a more service-centric model, when they start doing remote maintenance, they see that every installation is unique, and they have to adapt to those new conditions. Another thing that you typically realize is that, darn, then we don't have the data. You lack the data, especially for that individual installation. And you will also realize that typically the conditions change over time. Like one installation can have one behavior at one point in time, but it changes over time due to different circumstances, which is why we see that you have to take more of an iterative approach to how you work with this kind of intelligence. And what we are talking about, what you're seeing here, is very focused on automation, making automated decisions, automated insights that help in setting up different configurations, whatever it might be. But you're also generating some really valuable data, insights that you can send up to the cloud for further processing. Analytics, which is more of a reactive than a proactive approach, is really benefiting from having good data instead of big data. And I think that what we will see, which is a very natural development, is that you will apply intelligence at all levels, starting close to the source where you can do this kind of individual learning and insights. And then for every aggregation level, you're going to add another level of intelligence. That's how we predict and see that things will evolve. So our value proposition, Sebastian, at Ekkono, is that we help expedite the implementation of smart and intelligent features. So a very leading question. What is your experience from this project?
Well, yeah, I mean, it was a really positive project. I mean, it was a complex problem that we set, Ekkono, and we wanted to challenge you guys and see what the solution was, and then and that, you know, gave us some insight into what the working relationship would be, and you know, we're really pleased with that, and hence kind of we're sort of on this call today. I think, you know, one of the things that I really like about Ekkono, and one of the reasons that we're sort of continuing to work with Ekkono, is we don't always want the answers to be given to us. And so sometimes it's really helpful to just be given the tools, because actually, you know, hospitals are full of fairly smart people, and actually, as Jon was saying, every situation is unique, every patient is unique, every different surgery operation carries with it different risks. And so applying kind of one size fits all, or these quite broad brush approaches, it's not actually really what we're looking for, because we need that flexibility. And if you kind of give us the tools and we understand why each situation is unique, then that can really generate some insight that actually makes a difference to us. Because often when we see machine learning or AI applied in healthcare, it often doesn't make a lot of difference to the clinician and their ability to make a decision, because it's too generic. And so these tools, you know, and the flexibility that we've got, you know, we're working with Ekkono on this in the future, is to just try and empower us to use those tools to benefit patients.
So there you have it. Good summary. We're really happy to have Penn Medtech as a customer and using our technology to save life, just like we have other customers that are using it to kind of extend life on their products by doing predictive and proactive maintenance, and also saving the environment by running them as energy efficient as possible. That's what we do. Not a small feat, but we're up for it. Thank you.
Wonderful. Wonderful, Jon. Thank you. And thank you, Sebastian.
Thank you.
So thank you. You've been great. You're through the race. You've done it with grace, I must say. I guess you are as enthusiastic as I am. I get energized like crazy